Entropy begins with a simple idea. How do we measure randomness? We all have a common sense of what is random and what is not. Let's take a look at these three boxes. If these are free particles, A looks impossible, B looks very unusual, and C looks quite random. Let's begin the idea of how we quantify the randomness that we see. Starting with this example. Here is a smart idea. We can partition the box into two parts. If the particles are random, our intuition says there will roughly be the same number of particles on the left and on the right. But now we need to quantify this. Let's say the total number of particles is n. The number of particles on the left is k, which leaves n minus k particles on the right. In this case, we only distinguish the left from the right. So we can think of randomness as assigning k out of n particles to the left side and assigning the rest of the particles to the right side. This can be translated into equations. We define omega of k to be the number of possible arrangements with k particles on the left. That is given by n choose k, which can be expanded into a ratio involving factorials. In this example, there are 100 particles in total, with 55 particles on the left and 45 particles on the right. Omega of k can be represented with a histogram that describes the number of arrangements. The higher the bar, the more arrangements there are. You see, the chance of observing 55 particles on the left is quite decent. For the other configuration that we saw, suppose we have 88 particles on the left. That number of arrangement, omega, would be much smaller. And if we have all 100 particles on the left, the number of arrangements would be even smaller. In fact, in this case, it is exactly 1. Omega is, in fact, closely related to probability. We just need to divide by the total number of arrangements. We think each configuration is equally likely. If we compare the three examples, the probability of k equals to 55 is about 4.8%. The probability of k equals to 88 is about 8.3 times 10 to the negative 16, which is extremely rare for free particles in a box. And the probability of k equals to 100 is about 7.9 times 10 to the negative 31. So this is why, in reality, we would never observe 100 out of 100 particles on the left. This is literally the probability of guessing 100 coin flips correctly in a row. From these examples, we see that omega can quantify the randomness of particles. But there is a big limitation. We do not distinguish what happens inside the left and right partitions. In other words, if we take a look at these two examples in here, they would have the same omega of k, because they both have 50 particles on the left and 50 particles on the right. But you'll see that one is much more random than the other. This shows that just looking at one particular partition is not enough to quantify the total randomness of the system. For this particular example, the randomness of the system can be revealed again if we apply a different partition. Therefore, to extend what omega can do, we need to work for any reasonable partitions. So to check the randomness of the system, we need to look at partitions. From one partition, we can calculate 1 omega. But here is the challenge. To really check the randomness of the whole system, we will need to check many omegas. If the system is truly random, they should all be reasonably large. This feels difficult, because there are infinite many ways to partition the box. What we really want is one magical number that tells us whether the whole system is random. And remarkably, omega actually works. In fact, the total number of arrangements of the system is equal to the product of the parts. So let's consider partitioning the box into 3 regions. The total number of arrangements is given by this expression. Now here is the key idea. We can build a larger partition step by step from smaller ones. First, we combine region 1 and region 2. This gives us 1 omega, which counts the number of ways particles can be arranged between the region 1 and region 2. Next, we combine region 3 with the merged region consists of 1 and 2. This gives us another omega. The remarkable thing is that the product of these 2 omegas equals to the omega of the total system after the factorial cancels. These omega and factorial expressions may feel a little bit dense, but the message is quite clear. Partition can build up one at a time, and omega simply multiplies. This product relationship of omega is key to solving the earlier challenge. Using the product relationship of omega, we can show that omega total remains constant regardless of how we partition the system. When we have a box of free particles, first we can break it down into finer grids. Then we can merge a pair of small grids at a time. Each time, we add a small grid into the merge, which gives us an omega. And omega total will equal to the product of these smaller omegas. And here's another important thing. The order of the merging process does not matter. For example, we can first merge the smaller grids into 2 regions, the left half and the right half. Then we can merge the 2 to get the omega total. Or we can merge the smaller grids into these 3 arbitrary regions. Then we merge the 3. Importantly, we will obtain the same omega total in either case. Now, we can resolve the earlier challenge. Omega total is the one number we can check for the randomness of the whole system. If omega total is high, the system is random. And if any particular partition gives a low omega, it will lower the omega total through the product. Based on what we have learned so far, omega seems to be a solid choice for quantifying randomness. But we can make it even better. To bring out entropy, we just need one more step. It is a simple but a genius idea. We take the log of omega. By taking the log, we convert the product into a sum. So the sum of the parts equals the total in the log space, which is much more convenient to work with than the product. Informally speaking, randomness can be summed. When we have many partitions, we can now sum over the log omega of each partition merge to get the total log omega. By doing this, entropy now enters the game, because log omega equals to n times entropy. N is the total number of particles, and in here, n is a constant. This is a very important fact, but the proof is not central to the conceptual idea we are trying to uncover. You may pause the video if you are interested. The key step is to approximate the factorial with Stirling's approximation. At the end, we get the formula for entropy. H equals to 1 over the number of particles times log omega. That equals to the sum of P times log P. A cool thing about entropy is that the equation is no longer directly about the number of particles anymore. To quantify the randomness of the system, we only need these probabilities, which are the percentage of particles in each partition. So just like log omega, entropy can be merged using a sum. The algebra here is mostly bookkeeping, so don't worry about following every symbol. To see how it works, we start with the relationship for log omega total, which equals to the sum of two merges. Then we can replace log omega with the number of particles times entropy. For the total entropy of the system, we divide log omega by the total number of particles n. Then it becomes a sum of smaller entropies. But be careful, now we need weights for the smaller entropies. These weights are based on the probability, or the percentage of particles in each partition. And just like omega, the total entropy stays the same regardless of how we partition the system. We can express it by summing over the entropy of small merges one at a time. And we can perform this in any arbitrary order. So to sum up how we reach the formula of entropy, the motivation is that we want the full entropy to stay the same, even when we describe the system through different partitions. We started with the number of arrangements, omega, and found that omega total equals to the product of the parts. Then taking the log converts this product into a sum, and we show that log omega is proportional to entropy. So here's one sentence to remember all this. Entropy lets us build total randomness by adding the parts. But here's a subtle point. The grids themselves do not carry entropy. Entropy comes from merging grids, not from individual grid cells. Each merge contributes its own entropy, and the total entropy is obtained by adding those contributions together. Entropy is a truly remarkable quantity. The exact same formula is used both in physics and in information theory. For the motivation we just saw, this is the statistical physics view of entropy. We obtain the formula by reasoning about the randomness of the particles in the system. For the information theory view of entropy, we just need to look at the same system from a different perspective. We can reason about the partitions, which can be thought of as the information we can learn about the system. Let's start with an example by considering the following three partitions. We separate the box by different amounts. Then, using the entropy formula we just derived, we found that the entropy of the 0-1 partition is 0. The entropy of a quarter and 3/4 partition is 0.56, and the entropy of a half and half partition is 0.69. This interpretation of entropy is very important to modern information theory and data science, but we need to slow down a little in here. What do these numbers mean? Namely, how are they related to the total entropy we derived? First, let's bring back the formula of the total entropy. This is the equation we can trust. For this particular example, we sum over 3 terms because we need to perform 3 merges for these 4 partitions. But what is its relationship with one of the earlier examples we saw? So let's bring in an example, say a quarter and 3/4 partition. This corresponds to the merging of the region 1 and the region 2, 3, 4 combined. So see, This particular entropy only accounts for one of the terms of the total entropy. A very cool way to look at this is that a partition can give us information about the system. The total entropy is the total hidden information in this description. The entropy given by this partition is a part of the information that is visible to us. But you see, there are two entropy terms that are invisible to us because there are two more grids we do not get to observe. In other words, the total entropy can be divided into the visible part and the invisible part. So the visible entropy is smaller than the whole entropy. It is a part revealed by the partition we are able to observe. And this is how we interpret entropy in information theory. Using this interpretation, we can look at the other two examples. For each case, we have some visible entropy plus some invisible entropy. When we partition with 0 and 1, the visible entropy is 0 because all the information is hidden inside the 1 partition. The invisible part sums to 1.39. For the quarter and three-quarter partition, we have 0.56 visible entropy and 0.83 visible entropy. For the half and half partition, the visible entropy and the invisible entropy are both equal to 0.69. This is the case when visible entropy is maximized. Across all three cases, the total entropy stays the same, but the allocation differs. We obtain the most information when dividing the system into equal halves, and we obtain no information when dividing the system into 0 and 1. This should match our intuition. So to sum up what we have learned, the total entropy of the system can be divided into what is visible to us and what remains invisible. This is not just a mathematical trick. Entropy sits near the center of some of the deepest philosophy of reality. What information is visible and what information is hidden? Perhaps this is the deepest lesson. Entropy is not just about disorder or the randomness of the system. It is about what is hidden from the way we observe reality.